an interesting point is that people confuse complexity with complication. Okay, complicated problems need complicated solutions. Complex problems need simple solutions. I think it's an interesting mix. It's called 5 billion hectares of hope. Okay, so the idea is there's 5 billion hectares of degraded and desertifying grazing land on the planet. Before we get into that, we'll just address a couple of questions. First one is, can the human brain actually cope with climate change? Genetically and in our evolutionary times, can we actually cope with what this is about? Second thing is, a big question is one a big number? Well, just our desperate desire for technology. We desperately look for a technological solution to problems. And finally, apologies to Bill Clinton, it's the ecology stupid. Dealing with climate change, why our brains don't help. And as Shani mentioned it earlier, we'll build to it, we have a fear of the unknown and the unusual. Okay, so as soon as something's unknown or unusual to us, we're scared of it. There's pretty good reasons for that evolutionary, because if we didn't know what it was likely to try and kill us or eat us. So there's a reason that we're a little bit concerned about that. We then have, as was mentioned, simplistic linear thinking. We are desperate to link the effects that we see with a cause. Okay, as soon as we can link the effect with a cause, with one single cause, what we've got is no longer unknown or unusual. So we try to make the connection really quickly. We have difficulty coping with really big numbers. Okay, millions, billions, trillions. Okay, it gets scary. And you look at what happened with the global financial crisis. You've got 22-year-old kids playing with really, really big numbers, and there's all zeros, and it just went messy. We are absolutely hopeless with compound growth. Okay, so something going up by 1 or 2% a year, we have this desperate need for the GDP to increase by 3 or 4%. You look at a whole lot of projections, and all of a sudden, the amount of money we're spending on house prices going up 10% per annum forever. Okay, all of a sudden your house is going to cost you the entire production of the world. It can't happen, it's got to stop somewhere. This one's really scary in terms of dealing with climate change, because the whole carbon tax, great big tax on everything, and the economic part of it. Human beings are loss averse. What that means is that we are far more concerned with hanging on to what we've got than with getting something far more valuable down the track. Okay? What that means is we thus normally act irrationally when making economic decisions. Okay, so our starting point is we act irrationally, and climate change is talking about cost benefits and that. Let's start with some factors. This is Adam Neiman, a guy in the UK, did this incredible little graphic about the world to give us an idea of what we're actually dealing with. Okay, when you look outside, it seems big and limitless. Then on the left-hand side is all the water in the earth on the world put into the same at sea level pressure and temperature, and on the right is all the air at sea level pressure and temperature. Okay. Now the thing is, if the air was actually at the same concentration as down as a liquid, you'd have to condense it 800 times, and it'd be 1/500th the size of what you're looking at. So that's what we're actually dealing with. There's a description of the Earth given as a big ball of iron, some rock, surrounded by a really, really thin layer of water, air, and dangerous animals. That's probably exactly what that is. Okay. Why our brains don't help? We have simplistic linear thinking. Okay. A, B, C. That gets greenhouse gases are damaging to life on Earth. So if greenhouse gases are damaging to life on Earth, we need to get rid of greenhouse gases. As soon as we need to get rid of greenhouse gases, we have carbon pollution reduction schemes. We call it carbon pollution. That means that sources are bad and sinks are good. Okay, so that's really simplistic thinking. What follows from that is that all greenhouse gases are bad. So if all greenhouse gases are bad and methane is a greenhouse gas, then if cows emit methane, cows are bad. Okay? And at that point, you ask somebody anything past that, you'll find that is the full depth of their knowledge of the topic. Okay, they're opposed to cattle, they're opposed to ruminant animals, they're opposed to agriculture, and that's about the level of depth that they get to. What's the reality? What we actually need is complex cyclical thinking. As Ashani said, we are dealing with a cycle. If we're dealing with complex cyclical thinking, greenhouse gases are essential to life on Earth. Absent greenhouse gases, we would be a cold and lifeless rock. Greenhouse gas is the only thing that keep the average temperature of the Earth at positive 15 degrees. Without them, we'd be at minus 19. Okay, there's not too much happens at minus 19 degrees. What we've done is we've overloaded the system, and the cycle needs to be rebalanced. Now, if you start thinking in cycles, cows are a ruminant animal. All of those are ruminant animals. Ruminant animals evolved in the Miocene period, which is between 10 and 26 million years ago. They've been on the planet for millions of years. There have been billions of them. All the methane's going somewhere. What's happening to it? Okay, so just think about that for a little bit further. Hold the thought that these things are actually cycling carbon. Okay. What do we got? We've got 280 parts per million of CO2 in the atmosphere at the moment. Well, we had 280, before the Industrial Revolution. We're about 393 at today's date, and people are saying we're heading to 550. Okay, so those are the numbers we're dealing with. 1 part per million of what? Okay, so let's have a look at what the 1 part per million is. It's 1 part per million of atmospheric volume of carbon dioxide. Okay, so that's the main thing that the concern's about. Carbon dioxide is 1 part carbon and 2 parts oxygen. Pretty straightforward. I'm a fan of both of them. As Ashani said, she's got about 13 a bit kilos of carbon in her. I've made a substantially bigger contribution of carbon store than that. Okay. And oxygen, I'm also pretty happy with oxygen. Okay. Carbon dioxide is the molecule then weighs 44, the molecular weight. So there's a few facts and numbers here that I think are important to get a base, because the carbon molecule weighs 12 and the oxygen molecule weighs 16. Okay, so carbon's 12/44. So when you'll see carbon or carbon dioxide equivalents, you'll see that the carbon dioxide equivalents are 3.67 times the number of the carbon because of that ratio. If we got 550 parts per million, if we're heading towards 550 parts per million, okay, and we were at 280, we've got to start getting some of this out. Okay, so if we simply stop, we stop burning fossil fuels today, we go to wind power, solar power, and it's all peace, love, and mung beans, etc. What we end up with is we still go over the cliff, we just go over the cliff slower. We actually need to get something into reverse. So they're talking about moving carbon dioxide out of the atmosphere. Now, with geological carbon capture and storage, it stores the whole carbon dioxide molecule. Biological carbon capture and storage, which is green growing plants, splits off the oxygen and just stores the carbon. Okay. Now, there's some reasons that that's important. Let's have a look at some interesting numbers. So at room temperature and pressure, which is where we are today, carbon dioxide's a gas, okay, and 1 kilogram of it has a volume of 505 litres. Okay, so a couple of 44-gallon drums or a couple of wheelie bins, 1 kilogram of carbon dioxide takes that much space. At room temperature and 1 atmosphere of pressure, carbon, however, think about the graphite in your pencil, is a solid, and 1 kilogram of it is only 0.44 of a litre. That means that to store at room temperature and pressure, 1 atmosphere of carbon, or carbon dioxide, is going to take 1,100 times as much space as 1 kilogram of carbon. Okay, where does this start to come into some things that matter in terms of the way we structure things? So with geological carbon capture and storage, okay, to store it at room temperature, it requires massive amounts of energy. 20 to 30% of all the energy from the power station that it produces gets chewed up actually squishing the stuff down and pushing it underground. Okay, that's why the Chinese aren't particularly interested in it, because they're saying we're going to try to have efficient coal-fired power stations. If we put one of these things on, we've basically got to build 4 power stations to get 3 power stations worth of energy. To store carbon as a solid at room temperature, however, requires sunlight and green leaves. So it's a far more efficient process. Is 1 a big number? 1 part per million volume of the atmosphere is 7.8 billion tonnes of carbon dioxide. 7.8 billion tonnes of carbon dioxide, remember that little calculation? The conversion we do is 2.1 billion tonnes of carbon. What that means is for each time the CO2 concentration goes up by 1 part per million, there's another 2.1 billion tonnes of carbon have gone up into the air. 2.1 billion tonnes of carbon is a solid block of graphite, 1 kilometre long, 1 kilometre high, and 1 kilometre thick. Okay, how big is that? It turns out to be about that big. So that thing is about 1 cubic kilometre. Now what that means is if every time the CO2 concentration went up by 1 part per million, instead of it going up as a colourless, odourless gas, one of those popped up over a city, we'll be taking a little bit more attention to it. Okay, so if there were 270 more of those floating around over New York and London and Sydney, just hovering there, I think people would be taking this a little bit more seriously. Okay, so have we got a materials handling issue? Are we looking at this in terms of physically moving stuff around? So if the pre-industrial level of CO2 was 280 parts per million and we're at 393 and heading towards 550, we've got to get back down again, which means that we've got to take some out. So 270 parts per million have to come back out of the atmosphere. Okay. So remember, 1 part per million by volume is 7.8 billion tonnes of carbon dioxide. 270 of those is 2.1 trillion tonnes. This is where our billions, millions, trillions is. So we've got 2.1 trillion tonnes of carbon dioxide have to come back out. 2.1 trillion tonnes of carbon dioxide is 575 billion tonnes of carbon. That's the solid we've got to remove. How much is 575 billion tonnes? Okay. Australia's coal exports in 2010 were 298 million tonnes. So all those ships lined up and all those trains and all those miners getting paid all that money pushed 298 million tonnes out. Total world coal trade, all the coal that gets shipped around the world is 938 million tonnes. And the total world coal consumption was 6.2 billion tonnes. That means that the amount of carbon that we have to pull back out of the atmosphere if things keep going is about 1,900 years of Australia's coal exports, 613 years of the total world coal trade, or 93 years of total world coal consumption. Now, the interesting thing with that is that how many years are people saying we've got before we can we need to address this thing before we get to irreversible climate change. Okay, so the amount of stuff we've got to pull back out is 93 years worth of total world coal consumption. It's a pretty serious number. This is where the hope comes in. Okay? This is atmospheric carbon dioxide. This is the Keeling curve. This is the measurements that first highlighted the problems that we've got. And as you can see, it goes from bottom left to top right, and it goes up pretty steadily. And CO2 concentrations are increasing. Okay, so it's steadily heading up, and it's not a particularly happy story. Let's have a look at the little red line. What's the little red line? The red line is the annual cycle. Okay, so it goes up and it comes down every year. It goes up. Unfortunately, it goes up a little bit more, and then it comes down. So it's not coming back to the same base. But if you have a look at it, each year it's cycling by about 7 parts per million. Okay, so if you look in the bottom corner, you'll see there's a cycle there. What that cycle is the annual growth and dropping of the deciduous leaves on the boreal forest up in the top of the northern hemisphere. So all those plants that actually grow in spring and the leaves drop off in summer. They grow in spring, they drop off in summer. Okay, so 7 parts per million, those plants are shifting each year. 7 parts per million is 15 billion tonnes of carbon. Okay, 50 years of Australia's coal exports, 16 years of total coal trade, and 2.4 years of total world coal consumption. So all those little plants growing their leaves each year and dropping their leaves are pulling back and moving 15 billion tonnes of carbon. Okay, so there's a natural process out there that we're not involved with, other than negatively, that is moving that volume of material. And this is where Ashani said earlier that if the cycle didn't happen and if there weren't processes to release carbon, okay, within like the plant community pulls out 8% of carbon dioxide every year, land-based plants, which means that if we didn't have ruminant animals or breakdown or oxidation or whatever's happening to cycle the material back up, in 12 years there would be no carbon dioxide in the atmosphere. So the area that's actually doing that is the boreal forest part. Does that point? No. Which is across the top. Okay, so if you think about the globe, you've got the white bit at the top and the white bit at the bottom. You've got a big green stripe in the middle. You've then got the two, some brown stripes of the grasslands. And the temperate forest, which is the forest and the deciduous forest where the trees are growing and dropping their leaves, is that little strip across the top. So there's not much of the earth is actually involved in moving 15 billion tonnes of carbon a year. What does carbon look like in nature? Okay, so I'm partly carbon. What else is carbon? Most people think of this. Okay, the biggest tree you've ever seen. Okay, it's a great big lump. It's a couple 100 feet tall. It's the size of the room at the base. It's big. It's heavy. It's weighed. You can hit it with a bulldozer, and it's made of stuff. And it started off as a tiny little seed that big. Okay, where did all the stuff in the tree come from? Okay, a lot of people not that long ago would say, oh, it came out of the ground. As Ashani's mentioned, most of it is atmospheric carbon dioxide. So that tree is basically solidified carbon dioxide. The interesting thing is, so is this, grass plants. Now with a tree, what you see above ground is pretty much mirrored by what you see below ground. Okay, so the mass of the whole plant is about half above and half below. Interesting thing with grass plants is about the balance is actually 1 to 4, so there's about 4 times as much organic material below ground as there is above ground. Okay, that's why a hectare of healthy functioning perennial pasture can contain more carbon than a hectare of tropical rainforest. The reason is that the gaps between the trees versus the soil. That plant also is producing, as Ashani mentioned, something like 200 different organic compounds that are being released out of the root system into the soil. So, and all of those contain carbon. That's why we've got 5 billion hectares of hope, because we've got 5 billion hectares of seasonally dry grassland on the planet. If we change the management of that seasonally dry grasslands, what could happen? Unfortunately, at the moment, a lot of it looks like that. So any of the farmers in the room or anybody who's travelled, where is that? Where could that be? Yeah, not too far from here. Okay. There's another spot, which again could be anywhere on the planet. There's another spot. Why do they look like that? And people will say, oh, it's drought, it's overgrazing, it's poor management, it's a whole range of reasons. Okay. The interesting thing is that that's next door on the same day. And that's further down the same creek on the same day. And that's the river on the adjoining property on the same day. The top one's the Sonora Desert, Mexico. The middle one's Day Creek, Arizona. The bottom one's a riverbed in Zimbabwe. They're the same areas, they're the same rainfalls, they're the same soils, they're the same plant species, they're the same season. The pictures are taken on the same day. There's no irrigation, there's no chemicals, there's no fertiliser, there's no artificial anything. The area on the right has more livestock running on it per hectare in total than the area on the left. It also has far more wildlife. Okay? The only difference is the way the places are managed. Livestock in those areas get managed to increase the land's ability to absorb and hold water, okay? To build new soil, to help new plants start, to increase forage production, biodiversity, store carbon. These ones, they don't. Okay, so in these ones, when the management is the other way, what happens is the water doesn't stay in there, the whole process starts to go into reverse, and we actually release carbon. Grass plants are in proportion to its top, and in proportion, this is the bit that scares my kids because Dad gets excited talking about how grass grows, but a grass plant is in proportion. Okay, so a little tiny root system can't get great big leaves going, little tiny leaf system can't get great big roots going. This is an experiment that was done where the plants were kept trimmed at the same size. So the ones on the left were kept trimmed constantly, as if there were sheep or cattle in the paddock constantly grazing. You can see what happens to the grass plant. The ones on the right, it was allowed to express itself. All of that extra material is organic carbon. In nature, what nature wants in these ecosystems, think about the Serengeti as probably one of the last remaining healthy functioning ecosystems. What you'll see in the Serengeti is one small number of large herds. Okay, so there's a great big number there's a lot of animals in one herd. That herd's constantly moving. That's the migration of the wildebeest and the Serengeti. They move through two countries. They move hundreds of kilometres each year. But they're kept bunched up. While they'd like to take their time and spread out, they're kept bunched up. The reason is the edge of herds are dangerous. So the animals are all kept bunched up. What that means is you get that sort of an effect. Now, in a situation like that, you look at that number of animals could not be sustained on that landscape if they were stuck there. They've got to move on. Okay, they're in an area for a short period of time, hours or days at the most. They'll come in, they'll dung, they'll trample, they'll heavily impact, and they'll move on, and they won't come back for months or years at a time. What that does, with the grass plant being in balance, is they'll come in and they'll chomp the plant on the right. Once they chomp the plant on the right, what it does, to get back into balance, it sloughs off material. Okay, and that material is carbon going back into the soil. They then move off and allow the plants time to recover. Now, when the plants get time to recover, they regrow, and they don't regrow pulling the material out of the ground, they pull the carbon out of the atmosphere. So what you've got is a carbon pump, boom, pumping the carbon into the soil. Soil scientist said, I don't see why people don't get this. I said, what do you mean? He said, well, the whole soil, plant's pumping carbon into the soil. He said, carbon is black, the element carbon is black, and dirt gets darker. So there's a soil profile. In the Serengeti, wildebeest do that. Absent wildebeest, and we can't control wildebeest, that's some friends out on the Western Plains. So if you look at the behaviour of the animal, it's almost exactly the same. Some simple maths behind soil carbon. You follow through that, a hectare of soil, increase soil organic matter, and you come back with 100 tonnes of carbon per atmospheric CO2 sequester for each 1% increase in organic matter. That's the area in Australia. The numbers Australia can sequester 900 million tonnes, where a total emissions are 600 million tonnes. The IPCC has identified that there's 1 to 4 billion tonnes per annum can be sequestered. The UNFCCC has said that something like 70 or 80% of all the capacity for sequestration rests with soil carbon from grazing areas. So it's the ecology stupid. Now, what actually happens is that human beings reduce biodiversity, and this reduces biomass. How do we reduce biodiversity? In a grazing situation, or in a tribal situation, what we do is we get rid of predators because we don't want them killing us or killing our animals. Shani mentioned the number of microbes and bacteria that are in a handful of healthy soil. Okay, you tell people in the city that, they'll try and spray the soil. Think about the number of ads you see where spray this, spray that, clean this, wipe that. We take out biodiversity. You look at all the crops around here and we plant 1,000 hectares of one crop or this crop or that crop. So there's no biodiversity. Reducing biodiversity reduces biomass, and that alters several crucial processes in a logical progression. There's actually a hierarchy of ecosystem functionality which goes a little bit like this. So we'll rip through this. On the way down, okay, we reduce biodiversity. Reducing biodiversity reduces biomass, mainly plant cover. Reducing plant cover reduces photosynthesis. Reducing photosynthesis reduces carbon uptake and manufacture of oxygen, which reduces the accumulation of organic matter. Less organic matter means a disruption in nutrient cycling. Nutrient cycling disruption means a reduction in fertility. Reduces the infiltration or retention of rainfall, which changes the soil moisture, which changes the relative humidity, which changes weather, which results in changes in climate. Weather's what we're getting today, climate's what we have over the next 50 to 100 years. Okay. The interesting thing is on the way back, all that stuff bolts on, all that stuff's locked in together. But on the way back, it would look like this. What would we need to do to reverse that? What if we increase biodiversity? What if we just increase biodiversity? Well, that would increase biomass, which is plant cover. If we increase plant cover, we increase photosynthesis. If we increase photosynthesis, we increase the carbon uptake and the oxygen release, which increases the accumulation of organic matter, which restores nutrient cycling, which increases fertility, increases the infiltration and retention of rainfall, results in positive changes in soil moisture, positive changes in relative humidity, which result in positive changes in weather, result in positive changes in climate. So what happens on the way down can happen on the way back, and we can influence both of those. If we change the management, we change the land. Globally, we've got 5 billion hectares of grassland that we can do something with. So, thank you. Sure.